purpose of this video is to help you learn how to use the JET aircraft design synthesis and analysis software by demonstrating how to use the software to optimize an airplane for a particular design mission. The aircraft we're going to optimize is the F-22 Raptor prototype, and the design mission we're going to optimize it for is that aircraft's actual design mission, an offensive counter-air supercruising mission with a 250 nautical mile radius. Now, the F-22 was not optimized just for that mission. The aircraft was a compromise, and in particular, it was also optimized for close-in air combat maneuvering. And we know the F-22 does that very well. So one of the things we might learn from this exercise is what could have been gained by optimizing the airplane just for supercruise and just for the supercruising mission, and also perhaps what might have been lost. So we'll start. We notice in our software we've modeled the F-22 here in the left side in the geometry modeling interface. And on the upper right we've modeled the aircraft's final design requirements, constraints, and the constraint diagram that results from them. And then down on the lower right we've modeled that supercruising offensive counter-air design mission. We've modeled the payload of 6 AIM-120s and 2 AIM-9s, and the pilot as also a payload. And what the software tells us is that the F-22, as modeled in the software, could do what the real F-22 could do. So let's see what we can do to make it better. We're going to start by eliminating the horizontal tail. So a great big old thing. If you look on the weight tab, it weighs 1,000 pounds. And if we're not going to optimize for close-in air combat maneuvering, maybe we don't need it. Okay? If we get rid of 1,000 pounds of that, maybe we will be able to make a lighter airplane. Well, you might also be worried, though, that if I take away this huge stabilizing surface so far back on the airplane, that the aircraft will become very unstable longitudinally. And so let's see if that's what happens. We're going to type a very small number here in the area of the pitch control surface, and we're going to look to see how the static margin calculated in cell M10 changes. We never type zeros in JET for surface areas because that messes up the normalization of some of the coefficients, causes the spreadsheet to give nonsense answers. If we want to get rid of a surface, we just type a very small number for its area. So here we go. We're going to hit enter and watch cell M10. Well, isn't that interesting? The aircraft got more stable. In one sense it makes sense because we got rid of 1,000 pounds of weight very far aft on the airplane. So the CG moved forward and apparently got closer to the neutral point. But that means the neutral point didn't move much. And so why would that happen? Let's hit Control Z and let's see if we can investigate and see what's going on. Control Z, our surface is back. Let's go to the Arrow tab and look at the cell A40 where we calculate d epsilon d alpha, the rate of change of downwash and the position of the horizontal tail with respect to change in angle of attack of the aircraft. Notice the value is about 1. That means that for every 1 degree angle of attack increase for the aircraft, the downwash increases by 1 degree at the location of the horizontal tail. That means the angle of attack of the horizontal tail doesn't change. And that means the horizontal tail doesn't contribute to the aircraft's longitudinal stability. So that explains why the neutral point didn't move. But is that really true? Is that what happened on the real F-22? Well, speaking with the folks who designed that airplane, they said yes. The aircraft exhibited this same phenomenon where d epsilon d alpha was approximately 1 at the position of the horizontal tail. so the horizontal tail didn't contribute to longitudinal stability. What it did do, though, was give them excellent control authority for those close-in combat maneuvering and post-stall maneuvering and that sort of thing. And it also trimmed the aircraft, allowed it to rotate for takeoff, and allowed it to trim out the pitching moments from high lift devices. In fact, you'll notice here in column L that right now takeoff and landing CLmax is much higher than the clean CLmax because of those high lift devices. When we get rid of that horizontal tail, we won't be able to trim out the moments for those high lift devices anymore, so we won't be able to use them. And so these values will all be the same. So let's watch that happen. Again, we type in 0.001 in that cell, we hit enter, and sure enough the CLmaxes are all the same. We just can't trim out pitching moments from flaps, so we can't use the flaps. That affects our takeoff and landing constraints. We're now not meeting the landing constraint because we don't have as much CLmax, and we'll have to fix that at some point, but for now let's just move ahead. So how are we going to control the pitch attitude of the aircraft if we have no horizontal tail? How do we flare for landing and rotate for takeoff, and how do we trim the aircraft in flight? We're going to do it with elevons, and we're going to make those elevons from the ailerons that are currently modeled on the F-22. If you notice here in column E, the user interface for the ailerons, it's actually titled ailerons/elevons. And all we have to do to make these ailerons into elevons is put them further from the aircraft's longitudinal center of gravity location. In fact, what we're going to do is we're going to put them right on top of the flaps, since we can't use the flaps anyhow, and then we'll control those two things together. It'll just be a single moving control surface. So we do that by just referencing the cell, type an equals there, and click on the cell, and do that all the way down so that we will model the elevons as being exactly the same as the flaps were. Equals in each cell, and we can't do that in this cell because it's got an unusual format. It lets us display the 4-digit NACA code that defines our camber and thickness distribution. Because of that special format, we can't just type equals in there and reference the cell, so we just type in the number. For the rest of these, we can continue referencing the cells, and when we're done, we have elevons. Now let's give them a little more control authority, make the elevons bigger, and since we referenced the flap, we'll make all our changes in the flap column. Let's give it a little higher aspect ratio. We want the elevon to be near the trailing edge of the wing, so it's far from the CG, so it has a lot of control authority. Maybe just a little bit more aspect ratio. That's a good start at elevons. Notice now we do, as we promised, have 1,000 pounds of extra fuel, and the reason we do is because the way jet works is it calculates the weights of all the other aircraft components, the structure, the engines, the landing gear, and it totals this up to make an empty weight. Then it adds on the expendable payload and the permanent payload and subtracts that from the aircraft's takeoff gross weight. What's left must be fuel, and so that's how the fuel quantity is calculated. That way we're controlling how much fuel we carry by typing in a number for the aircraft takeoff gross weight. So we've got too much gas, so we'll make the takeoff gross weight less, 63,000. And we still have a little bit more, 62.8, because that lighter airplane burned less gas on the mission. Alright, so what else can we do to help this airplane be a more efficient supercruiser? Well, the fuselage is not very slender. It's a pretty chubby airplane for a supercruiser, and that's because if you want to do lots of post-stall maneuvering, you need all of your missiles close to the center of gravity, and so they put two weapons bays side by side almost on the aircraft center of gravity, and that was good for maneuvering but not so good for supercruise. So let's make the airplane more slender. Let's take those two weapons bays and put them one behind the other. Let's make the airplane longer but also not as wide, and that's going to dramatically reduce the wave drag for supercruise. So let's make this thing maybe 68 feet long, so there's room for two weapons bays. Let's make it only 6 feet wide, okay? And then let's hit regenerate, and you can watch what happens to the airplane. Also watch what happens to the A versus X plot as we make that airplane more slender. You see it's making the airplane into a ogive cylinder fuselage, and that dramatically cut down the fuel burn, and the smaller fuselage also weighs less, so we have quite a bit of extra gas. We've got 3,000 pounds of extra gas. But the area ruling doesn't look real good. There's this great big bump back here, so since we made a cylinder in the rear part of the airplane instead of that nicely tapered fuselage, let's go get that tapered fuselage and put that back. We still like the way the fuselage tapers in the vertical. So we go to another copy of the F-22 that we started with. We can scroll down here, and we'll start here with a height of 6 feet. See how it tapers down to 0. We're going to highlight those values and just copy them over and put them, paste them into our optimized F-22. Start there at row 44 and just paste them in, and you see that helped A versus X quite a bit. Another thing we can do to help A versus X is move our vertical tails back, and they're also not on the fuselage anymore because the fuselage got narrower. So let's move them back maybe to 49 feet or something like that, and that looks pretty good, and take them into 3 feet so they're touching the horizontal or the rear fuselage now. And what that did for CN beta is make it way too big, so we can make the vertical tails smaller and still keep a good value for CN beta. Alright, that's a little too low, but it'll probably get better. For one thing, we're going to work on the wings and increase the sweep, and that's going to help with the value of CN beta and with the value of CL beta and the ratio of those two here. We don't have quite enough volume yet, but we've got a lot of extra gas again, so let's get rid of that. The smaller fuselage weighs less, burns less gas, so we've got 5,000 pounds too much gas. So let's cut that by 5,000 pounds. We'll go to 57.8. In this cell, 57,800. And sure enough, we're good. We still have 1,500 pounds. Let's try 56. We still have enough gas. And notice now that we're meeting our takeoff and landing constraints. So by reducing weight, we were able to get back inside those constraints. Well, let's try to make this airplane even better. Let's sweep the wings more, make the wings more slender. So we'll sweep them back to 60 degrees so that they have a subsonic leading edge until they get all the way up to Mach 2. That's going to reduce drag, and sure it did. You can see it back here. But the greater sweep made the wings weigh more, and so that gave us less total fuel. So we're not actually having enough fuel to fly the mission now. Those wings aren't good for other reasons, like RCS. The trailing edge is not fuselage shielded at all. So let's make some more changes. Let's cut the aspect ratio maybe to 1.8. That's going to help. Makes it almost a delta wing. And then if we've got more than 45 degrees of sweep, we can actually cut the taper ratio down as low as we want. That limit on taper ratio of 0.21 is only for wings with less than 40 degrees of sweep, and that limit there is to avoid tip stall. But when you've got more than 45 degrees of sweep on a wing like this, you'll get leading edge vortices, and they'll take care of your tip stall problem. So let's get the taper ratio to 0.01, and now we've got a wing that looks like still a delta wing, but it looks like the horizontal or the trailing edges are going to be fuselage shielded, and that's good for RCS. Well, everything is happy over here. We saved another 2,000 pounds of gas, or we have 2,000 pounds of gas we don't need because we made the wing lighter by reducing the aspect ratio and taper ratio. So now we can get closer here. We've got 400 pounds extra, but we don't really need that. Still some more trouble on takeoff and landing, and that's because that lower aspect ratio swept wing doesn't generate as high a CL max. Well, we can fix that by changing the constraint. The actual requirement is to operate from a 6,000 foot runway. That means you need to be able to take off or accelerate to takeoff speed and then abort in the remaining runway. So we've got a stopping distance constraint and a takeoff constraint, and the two of those have to add up to 6,000 feet. Well, we're taking off in 1,500 feet, so that means that we could make this number a lot smaller and harmonize these two takeoff and landing constraints. The way we've got it set up, we're actually calculating the landing constraint by subtracting the takeoff constraint from 6,000. So if I make this 2,000, I'll get a much nicer looking, more harmonious balance between the takeoff and landing constraints. Now there's a couple things we notice here. The aircraft has a lot more thrust to weight ratio than the optimum. And I'm wondering at this point if we can get away with one engine. That'd be remarkable if we could. So let's give it a try. Let's try one engine, put a 1 in here, and yeah, we're not meeting anything yet. But look, by taking away the engine, we took away a lot of weight, and we now have 12,000 pounds of gas we don't need. So we can drop the weight by 12,000 pounds to 42,000. And some of our problems went away. We're making takeoff and landing no problem now. And we have just a little issue with meeting our desired Mach numbers at particular altitudes. Well, there's some other things we could do to help with that. We can push the verticals further back so that their AMAX is not coincident with the wing's AMAX, and that's going to help reduce AMAX. That's going to reduce wave drag, and that's going to reduce fuel burn. We've already got too much gas. We can cut this to 40,000 pounds. That's just going to help. And actually that solved our problem, but let's go ahead and move the verticals back a little bit further. Let's go 51. And now AMAX is a little less, and not only that, our verticals are too big, so let's cut them down in size again, maybe to 100. And that was a little too aggressive. Let's go 120. Okay, the other thing we notice is that the aircraft is too stable. Well, part of the problem is that the engines are too far forward. We made the fuselage longer, we didn't move the engines back. So let's move the inlets back maybe 7 feet. Let's put 25 in here. And then let's move the engines a few more feet by changing the distance from the inlets to the compressor face. Let's make that 26. Move it another 4 feet back. Static margin is now better. Our CN beta is about right. Our ratio of CN beta to CL beta is good. The only thing I notice is that the airplane, the wings are too big. And why I say that is the optimum point is over here to the right. Our wing loading is less, so that means our wing's too big for the gross weight we're at. Not only that, we have 1,000 pounds of gas we don't need, so let's cut this to 39,000. And that's going to make this problem even worse. So let's try creeping down on wing area. Let's go down to 750. And now you see that we're getting closer. We've got another 700 pounds of gas we don't need, so 38.3. And let's try 38. Not quite enough gas, but once again the wing's too big. Let's try 700. Okay, good. Our plus is very close to the circle. We have a little bit of extra gas. We can cut down to 37.8. And we haven't even tried changing our cruise altitude yet. Let's take a look at that really quick. We can save more gas by climbing higher. Let's see how much higher we can climb. 53,000. That worked, saved a little gas. 54,000. That worked. Let's try 55,000. Now, we should mention that in the old days, flying with a manned aircraft above 50,000 feet was not allowed. That's because in the case of a rapid decompression, the stresses, the physiological stresses on the human body would be too severe. But we know the F-22s fly above 50,000 feet. And the reason they can do that is they're wearing full body anti-G garments which squeeze their body, and they're also pressure breathing 100% oxygen which squeezes their body from the inside. And so the physiological effects, stresses from a rapid decompression are much reduced, and they feel like it's safe to fly above 50,000 feet in those particular aircraft. So let's take advantage of that. We're up to 55,000. When we're heavyweight, over here on the way back, we probably can go higher. Let's try 58,000. Let's try 60,000. And we saved 400 pounds of gas. 37.4. Okay. We've got a pretty nice looking airplane. There's a few things we can do to clean it up, but we're off to a good start. And at this point, let's see what we've accomplished. We can compare the price per airplane down here. $77 million for our single engine optimized YF-22. And we can compare that with the F-22 we started with at $125 million. We've saved almost $50 million an airplane, not quite cutting it in half, but we've dramatically reduced the cost, all by just optimizing it for the particular mission. And if we look at our constraint diagram, we're still able to meet all the constraints that the original YF-22 could meet. It's true, if we wanted to do close-in dogfight type combat maneuvering, this airplane would not be as good as the original YF-22. But it's arguable that doing close-in combat dogfight type maneuvering with a stealthy airplane is not really a good idea. This may be actually a wiser way to use a stealthy aircraft. And an airplane optimized for supercruise, where you get in there quick, you hit hard, and you get out fast. So at this point, we will declare victory. There's more work to do, but we'll do that in another video. We should ask ourselves, though, what have we done here? Have we tricked ourselves? Is the software lying to us? Could we really build an airplane that could perform like this on a single F-119? Turns out the answer is yes. This airplane looks a lot like an F-106, a Century Series fighter, supersonic on a single J75 engine that produces about 25,000 pounds of thrust in afterburner. Well, the F-119 is the same size as that engine, same diameter and shorter, and weighs less, and it produces 25,000 pounds of thrust in mil. The F-106 could go Mach 2.3 with that thrust, so we're betting that this airplane, which looks and has drag similar to an F-106 and weight similar to an F-106, could do the same thing on an F-119 in mil. So that's pretty darn good performance, and we can tell for sure that we're not tricking ourselves. We can compare weights with an F-106, we can compare drag with an F-106, and we know an F-119 would actually fit in an F-106. If we wanted to, we could put one in an old F-106 and prove it with a flight test. So the software is telling us the truth, and it has led us to a very attractive, optimized aircraft design.